Here is myLab2. Motion of a falling object. For this LAD I've used a piece of foam as an object and my NXT brick as a clever assistant. Here is a video I've captured with his help. Actually, I held my camera in vertical position, so the previous video was turned. Here, using the tracker application, I had this video how it was originally captured. The calibration stick is 2 meters. In the application I have used horizontal axis X instead of Y as it's more easy for copying to spreadsheet later. The axis X was negative in the right direction. Here is tracing. These are the results of my experiment. I noticed terminal time and distance. Here is the initial setup for the Python code of the computer model. The mass of my foam object is equal to 0.03 gram. The initial velocity and position are zeros. The delta t is 0.001. And firstly we assume that drag force is equal to 0, so the proportional constant b is equal to 0. We calculate gravity force one time as it is constant. We use calculation loop to calculate falling object positions. We use Newton's second law to calculate velocity and position for each iteration. For a first model we assume that net force is equal to weight, so drag force is equal to 0. Here are code for calculation due to Newton's second law. We have about 1000 iterations, but for a graph we don't need so many points. So I did a small trick. I use a counter and for writing data to output file. For each iteration I check module of n and write data if n is 0 by module 10. So I have about 100 points in output file. Now here is the model for case when the drag force is equal to 0. F net is equal to weight. Here is a chart of position of the data I got from application tracker and the model position. It is clear that model is faster than experiment. The explanation is that it is due to the fact I did not apply drag force. We can say that velocity of the model is always increasing. The experiment shows that in time the velocity of the object is constant and we see that position changing is linear. Here are formulas for the model with effect of drag. The magnitude of the drag force is proportional to the square of the object's speed. Direction of the drag force is opposite to the velocity. The vector of net force is equal to sum of gravity force and drag force vectors. Here code implementation of those formulas. The proportionality constant, b, for magnitude of drag force I have manually adjusted comparing final position of the model and experiment. Here is a video of the running model with the drag force. Here are all three graphs. The experimental position is the blue graph. We could see that the model with drag force, beige, predicts object position much better than the model with 0 drag force, red. Which models predict a terminal velocity? The model calculates velocity in each iteration. To build a velocity graph, we have to change the variable of distance to variable of velocity in right statement. Here is as it looks. As expected, the 0 drag model has linear growing velocity. So we could say that it does not have terminal velocity. The drag model has constant velocity in the end of time interval. So the drag force model predicts terminal velocity. Here is a question. Here are graphs of the models with 0 initial velocity and initial velocity equal -1. The graph with non-zero initial velocity is getting a constant value faster. This is explainable. The drag force is proportional to the square of velocity. So the net force becomes a constant faster if we have initial speed downward and we got constant velocity faster.